let's talk about the parameters that I'm going to measure in this video. Let me explain a little about each one so we can better understand each step. The operational room response curve is the value measured in decibels of the sound pressure level generated by audio monitors emitting a signal with the same amplitude at all frequencies, such as pink noise, for example, in bands of 1/3 of an octave or up to 1/48 of an octave. Among the various parameters examined in this video, we can highlight the importance of having values for this response curve within or very close to the acceptable tolerance range determined in the technical recommendations, such as EBU and ETU. In this video, we are going to measure frequency in band of 1/3 of an octave as recommended in the EBU TAC 3276. Another parameter is called, you're going to measure is the reverberation time, also here in the mix engineer position. Currently, there are several parameters that are derived from the reverberation time, which is defined as the time taken for a sound to decay 60 decibels below the initial level. It is usually measured in the range from 5 decibels to 25 decibels below the initial values and multiplied by 3. This is called T20, okay? Or 5 decibels to 35 decibels and multiplied by 2. And in this case, it's called T30, okay? This is equal to a sound decay of 1,000,000 times in relation to the original power. The EBU established value for the reverberation time between 0.2 and 0.4 seconds for control rooms in recording studios. So let's talk about two more parameters. One is called energy time curve, or just ETC, and a decay curve, also known as Schroeder's plot. In the case of a small environment, such as control room, each reflection is important in the outcome of the acoustic behavior at the reference listen position. These reflections can cause undesirable effects, such as comb filter, for example. In order to examine the behavior of these reflections, parameters such as energy time curve were proposed, with the intention of obtaining an accurate chart of energy decay time. Methods for this analysis were studied by Schroeder. In 1964, Schroeder presented the article New Method of Measuring Reverberation Time on AES. And in 1960s, Richard Hazard registered the patent of TEF, Time, Energy, Frequency, which used the energy time curve, the ETC, as part of the measurement system. You can find a lot of publications on the AES website. I certainly recommend you to visit and browse there. There's so many, there are a lot of articles about so many different subjects, audio, acoustics. You definitely should go. The energy time curve graphically presents the decay of energy over time, with the peaks in the curve allowing us to identify specific reflections in the environment. This way, it is possible to reposition objects and also the audio monitors. In order to obtain the ETC graph, a second signal is derived from the impulse response. This new signal is similar to the original, but there's a lag of 90 degrees. This means that when one signal is at the maximum value, the other one is at 0, and vice versa. The energy time curve is obtained by the sum of the RMS value of the two signals. The resulting chart shows the sound pressure level at different frequencies. The amplitude and frequency response of each reflection come from measuring impulse response through a Fourier transform. Measuring the reflections below 500 Hz can be difficult according to the EBU. Another way to analyze the reflections of an environment is through the chart. A chart that combines sound pressure level, as a function of time, frequency, and energy This chart is called Waterfall. Through the Waterfall graph, it is possible to analyze the decay of acoustical modes of low frequency in small rooms. The Schroeder's plot is more appropriate to understand the behavior of the reverberation time when the main objective is to evaluate the decay, the energy decay in the room. The energy time curve is better for identify distinctive reflections. The background noise in the case of a control room is any type of noise that is not coming from the audio monitors. Background noise in control room can be the equipment, the air conditioner, or the noise that penetrates in the control room from outside, called sound transmission.